Good morning, students. Today we are going to discuss few topics from chapter 6, electromagnetic induction. Already we have started this chapter. Now the topics which we are going to discuss, number one is your motional EMF. Now in last class we have said that whenever there is a variation of magnetic flux, induced EMF produces. So here is also we are trying to vary the magnetic flux, and for that we have taken this frame. And this is your U-shaped frame, and over this frame there is a movable wire SR. Now it is placed in the magnetic field B vector, and the symbol cross define that the magnetic field is perpendicular to the plane. Now what we will do here, we will try to vary the magnetic flux by pulling the wire SR with the velocity V. Now as SR is pulled with the velocity V, so what happens? The area of the loop changes. It means there is a variation of flux will occur, and as a result there will be induced EMF. So let me read out. The induced EMF produced due to the motion of a conductor through a uniform magnetic field is called motional EMF. Let me repeat. The induced EMF produced due to the motion of a conductor through a uniform magnetic field is called motional EMF. Now as we have said that if we vary the area by pulling the wire SR, definitely some change in flux will occur, and as a result induced EMF will produced as per our Faraday's Lenge's law. Now magnetic flux can be denoted by phi, is already we have discussed, that is your phi equal to BA, and A is your area. Now if we consider area of this loop at present, which is in the figure, that is your Lx, length into breadth. So when we pull the wire SR with a velocity V, what happens basically? X changes. Okay, X changes, it means area changes, but L remain fixed, because L is nothing but the length of the wire SR, you can say. So A equal to Lx, from Faraday's Lenge's law, E equal to minus d phi dt. Faraday's law is your E equal to d phi dt, and negative sign comes from Lenge's, because induced EMF opposes the change in flux. So E equal to minus d phi dt, so minus d dt, phi is your BA. So A is your Lx. So BL comes out, so it's your minus BL dx dt. Now dx dt or minus dx dt is nothing but the velocity, because you see if the velocity increases, x decreases, is not it? So that's why negative sign is there. So if V equal to minus dx dt, then it comes out E equal to BL V. So induced EMF is nothing but is your magnetic field, length of the conductor, and the velocity. So this is the topic. It's a very important for the numericals. Please go through this one. Now next topic which we are going to discuss is your motional EMF in a conducting rod rotated in a magnetic field. So here you see this is your OP, you can say, is a conducting rod which is rotated in the magnetic field. So when you rotate this wire or the rod OP by fixing one end O, so what will happen if you rotate it in the magnetic field? Definitely variation of the flux will occur, or you can say some kind of disturbance will occur in the magnetic field. Okay, now this disturbance in the figure we have not shown the magnetic field. You can show in your diagram. So let me to represent the magnetic field. So magnetic field you can show in the figure by giving symbol. Though we have not shown here, you can show. This is your magnetic field, V vector. So you have to show the magnetic field in the figure also. Now when you rotate this conducting rod by fixing one end O, So what happened, basically it creates some kind of disturbance in the magnetic field. It means some fluxes changes there, and due to the change in the flux there is an induced EMF. So let me go for the equation E equal to minus d phi dt, phi equal to BA. Already we have defined the flux. So number 3, for 2 pi angle, area is your pi L square, is not it? If we consider this figure for one complete rotation. So for angle theta, area corresponds is your pi L square by 2 pi into theta. So it's your half L square theta. So phi, here A is your half L square theta. So flux is your phi equal to B half L square theta. Now EMF as per the Faraday's Lenz law, E equal to minus d phi dt. So let us substitute phi, B by 2 L square theta, BL square by 2 d theta dt. Now d theta dt is your omega minus BL square to omega. So omega is your angular velocity by which you have rotated the rod, whose length is your L. So the magnitude, if you consider, equal to half BL square omega. So in the figure we have to definitely give the magnetic field notation, because you are rotating the rod in the magnetic field as per the topic. Now next topic, let me go for this one, self-induction or self-inductance. Now before starting this topic, or before going to the definition, this is your circuit diagram. It's a coil and the source is there and a key K. Now when you close the key K, what happens? Current starts rising. So this increase in current, what happens? Increases the magnetic flux. Now this increase in magnetic flux is nothing but some kind of change in flux. So what will happen? An induced EMF is produced, and as per the Lenz's law, this induced EMF opposes the rise in current. That's why when you close the key K, or key denoted basically by K symbol, when you close the key, it takes time to reaches the peak value. Now or current takes time to reaches its peak value. Similarly, when you open it, what happen? Decrease in current in occur. So there is a change in flux will occur due to the decrease in current. So this decrease in current induces an EMF and it opposes the decrease in current. So that's why if we open the key, it takes time to cease the current completely. So this property is nothing but some kind of inertia. So let me to repeat. Self-induction is the property of a coil by virtue of which it opposes the growth or decay of the current flowing through it. So this property is known as self-induction. Let me repeat. Self-induction is also known as inertia of electricity, as it opposes the growth or decay of the current in the circuit. Now mathematics part, if I be the current and phi be the flux linked with the coil, then definitely phi proportional to I. Okay, if a rise in current will be high, flux also high. So phi proportional to I, phi, and to bring equal, you have to bring one constant, where L is the coefficient of self-inductance, phi equal to Li. Induced EMF E equal to minus d phi dt minus d dt, phi is your Li, so minus L di dt. So this formula is very important for the numerical. We will try some numerical. So let me to repeat this diagram once again. When you close the key K, let me to give the symbol K, as I am telling repeatedly, K. When you close the key, what happens? Current starts rising. This increase in current produces increase in flux. So increase in flux is nothing but some kind of change in flux. As a result, what will happen? As per the Faraday's Lenz's law, an induced EMF will produce, and this EMF opposes the rise in current. That's why when you close the key K, it takes time to reach its current. It takes time for current takes time to reach its peak value. Similarly, when you open the key, current starts decreasing. So decrease in current causes a decrease in flux, and this change in flux induces an EMF. So induced EMF again opposes the decrease in current. So that's why when you open the key, current takes time to seizes its value, and this property is nothing but self-induction, and it is denoted, or you can say self-induction is nothing but some kind of electrical inertia. So this is all about. Please go through this topic and try to find out your doubt. Thank you.